This lesson deals with supplemental problem 10.2. You can find this problem in the ECE202 ebook in the Chapter 10 Supplemental Problem starting on page 2. Let's again take an example from ECE201. In particular, this is supplemental problem 7.2. And let's solve for the capacitor voltage in this circuit, but using Laplace transforms. Now what we've got here are two batteries, 3 resistors, a capacitor, and a single pole double throw switch that's in this position for a long time and then switches to this second position. Let's use our 5-step algorithm. First is to find the initial conditions of the reactive component, and that's our capacitor. So let's find the voltage across the capacitor when the switch has been in this position for a long time. Capacitor looks like an open circuit, and the voltage across the 24 ohm resistor is the same as the voltage across the capacitor, and so I could use a voltage divider to find that voltage. It would be 24 divided by 24 plus 16 times the voltage 12. That turns out to be 7.2 volts. Our second step is to transform into the S domain. Now when the switch is closed, the left-hand side of the circuit is no longer connected. What we've got then is the bottom part of this switch circuit, which is an 8 ohm resistor and a 9 volt battery, but that would be a step function in the S domain, so just 9 divided by S. Our capacitor is replaced by an impedance of 1 over SC. 1 over 0.33 microfarads turns out to be 3.03 times 10 to the 6th. Our initial condition was 7.2 volts, and that's a step function, and that's in series with the capacitor. Now the voltage across the capacitor is not this, but the voltage across the 24 ohm resistor. We're replacing the capacitor by this model. The next step is to do the S domain analysis. Since we have two sources, we could use superposition. Let's set the initial condition equal to 0, and let's solve for the voltage across the 24 ohm resistor, which we called V sub C. What we've got now is a capacitor of 0.33 microfarads in parallel with 24, in series with an 8 ohm resistor, and then a step function of 9 volts. So we can use voltage divider. Take the voltage across the parallel combination, voltage divided with the 8 ohms times our 9 volt step. Now the parallel combination, we could take the admittances and add them together and then take the reciprocal. So the resistor would be 1 over 24, and the capacitor would just be S times C, which is 0.33 micro times S. Let's multiply numerator and denominator by this term. So we're just left with a 1 in the numerator times 9. The denominator has an S, and then this term is just 1. And then multiplying this times 8, I have 8 over 24, and then 8 times 0.33 micro times S. Let's add these two together. This would be 24 over 24, so that'd be 32 over 24. And that's that term right over here. I'm going to pull out this 8 times 0.33 micro. So pulling that out in front, I'll be dividing by that for this term. Then I just have a 1 times S, and then I've got that term in front here. So multiplying this out and dividing it into 9 turns out to be 3.409 times 10 to the 6th. We have S, and then we have S plus the reciprocal of this times 32 over 24, and that turns out to be 505K. Now I'll set the 9 volt step equal to 0 and do the same process. Now the voltage across the 24 ohm resistor has an 8 ohm in parallel with it, and again forms a voltage divider with our capacitor. So that resistance over that resistance plus 1 over SC, and that would be 1 over 0.33 micro, which is 3.03 times 10 to the 6th. We're going to multiply that by our initial condition, which is a 7.2 volt step. 8 in parallel with 24 is the product over the sum. It turns out to be 6, so I've got 6 over here. Let's multiply through by S then. So I've got 6S, and then I've got 3.03 times 10 to the 6th. Could pull out the 6. So I have S plus 3.03K times 10 to the 6th divided by 6, and that's again 505K. The 6 and the 6 cancel. I got 7.2 in the numerator. So now I can add these two results by superposition. So I have the first term plus the second term. Got a common denominator of S plus 505K, and then multiply that also by S, and multiply this by S. That would give me 7.2 times S, and then 3.409 times 10 to the 6th. Step 4 is to perform a partial fraction expansion, so I could write this as some K1 over S and some K2 over S plus 505K. To find K1, we'll multiply our result times S and let S equal 0. So again, get term cancellation. And then I've got 3.409 times 10 to the 6th divided by 505K, and that's 6.75. Likewise, to find K2, we'll multiply by S plus 505K, our result of the sum of the two capacitor voltages, and then let S equal minus 505K. And again, we have a cancellation of terms. So I have 7.2 times minus 505K plus 3.409 times 10 to the 6th divided by minus 505K. That turns out to be 0.45. Step 5 is to find the inverse Laplace transform. So we've got K1 over S plus K2 over S plus 505K. This is just a step of 6.75 strength times U of t, constant of 0.45, and then 1 over S plus alpha is e to the minus alpha t, which would be a minus 505 times t. Okay, let's write this as a time constant. So I'll take the reciprocal of 505, and it turned out to be 1.98 micro. So our end result then would be 6.75 plus 450 milli times e to the minus t over 1.98 microseconds, and all this times u of t, and the units would be volts. To solve for the capacitor current, then we can repeat this same process again, but it would be easier to use the definition of I is equal to c dv dt, and just differentiate this last result. Let's do that. So our capacitor value is 0.33 micro. The derivative of 6.75 with respect to t is 0. Got a scalar in front of 450 milli, and then the derivative of e to the ax is a e to the ax, and so a would be equal to minus 1 over 1.98 micro. And then we got e to the minus ax left over. So multiplying this through this times this, divided by this, I get a minus 75 milli, times e to the minus t over tau, where tau is 1.98 microseconds, and the units here would be amps. This would be true for t greater than 0. I could use the u of t again. And this is supplemental problem 10.2.